In that case, this is a transition questions pretty clearly. For these transition questions, we do always want to make sure that we are trying to put the relationship between these two sentences in our own words and taking an elimination process from there. These questions are ones where we want to make sure that we're hitting very, very high accuracy eventually, because these skills of like understanding the relationship between sentences are foundational skills for many other question types on the test. So they're often like a good barometer for how well some of our background skills are going for the harder analysis questions. Can I ask you to talk me through your thought process for this one? Mm-hmm. They repudiate. Sorry, what was that? They repudiate. Okay. So one of the things I'm hearing pretty immediately is that we're not super understanding of the word repudiate. Is that correct? We don't have a great definition for that one. Okay. I'm not going to give the definition until we're through this question, but I want to talk about how we can infer the meaning of that after the fact. In any case, can I ask you to talk through your process of elimination from here? That said, is a transition that many people have struggled with. Couldn't tell you why this one in particular is so bad, but a lot of people just don't know the definition of it for whatever reason. I'm not going to talk about its definition just yet. If we can't eliminate it for now, then we'll keep thinking the final choice through, and we'll see if D is better or worse than a choice where we're uncertain of its meaning. I'm listening. And D is correct. Um, you've got the relationship between these sentences correct. Your understanding of the sentences themselves is a little bit flawed. So, first, let's talk about that said. That said, you can think of as just being however. So, you might say something like, Monish was missing a few vital definitions to work on this sentence. That said, other parts of his thought process were strong enough that he was still able to get it right. Let's take a look at a stronger understanding of what these sentences are saying, and then we'll also use that to infer what the word repudiate means. With this first sentence, I heard something about um, how groups of people can better use common resources than the government. Are they saying better than? Yes. The parentheticals aren't there to talk about better or worse. They're there to distinguish the people who use them from private entities and governments. They're so you know what group you're talking about. Now, what is the tragedy of the commons from the second sentence? And does the first sentence agree or disagree with this stating of the tragedy of the commons? It is providing a counterexample. Therefore, what do you think it means to repudiate something? Hmm? Yeah, absolutely. Hearing that similarity to refute is not coincidental in this case. They've both got the re prefix for the same reason. So, that right there is one of the ways where we can deduce the meaning of a word via osmosis, basically. By understanding everything in the surroundings of the word, you can understand what the word itself means. This is ideally not something that we have to do on the test, but it's also like how we learn words in general, right? Um, hello? Got it. Um, or what was I saying? Right. This sort of understanding language via osmosis, this is how we tend to learn words in general. For instance, I know that I tend to use a fair amount of words that my students are not terribly comfortable with. I use phrases like heuristic not infrequently. And I'd be pretty surprised if you knew what a heuristic was off the top of your head. Oh, you could have. That is one of the areas where you can learn about it. A heuristic is more specifically a method of understanding something. And there's often the assumption of a lot of what you're calling out there that it's not necessarily perfect, but it's something that you use to understand a situation quickly and imperfectly. and you can have more and less refined heuristics. The more refined it is, usually the more time it'll take, or the more resources it'll take in some capacity, but the more specificity it'll have in terms of its intent. Um, but I digress. Even if you didn't know what that word meant explicitly, it's the sort of word that you would learn just by it being used around you. Being able to pick up words that way, really, really powerful. Lord knows that I certainly did not generate my vocabulary by reading through the dictionary. I just developed my vocabulary by reading a lot of words. I just read a lot of books, man. I don't know what to tell you. Is there anything that you want to check in on this 23 or anything remaining in the reading section you'd like to check in on before we dial into the Math Module 2, Question 9? Got it, got it. So then, let's take a look at this question number 9. For this one, what's the first thing that you'd want to do? And you absolutely should. There are approximately 1 million reasons to draw pictures, and the better you are at drawing pictures, the more ways in which you can use them. For geometry, the really big upside of drawing pictures is that it lets you offload information so that you don't have to think about it all in your brain. I'm going to ask you to draw your picture first, and then I'm going to draw a picture in Adobe, and we'll see if we have drawn a similar picture. Do we have our basic picture drawn, or do you need a moment longer? Okay. And then is our picture looking something like this, where we've marked this angle as being 88 degrees. Excuse me, that's O in the middle. And marking RSO as X degrees. Is there anything else that you've annotated this figure with? Okay. Where would you go from here? Where's your brain pointing you towards? Mm-hmm. 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 If you could write another equation, it would be helpful, but that's a big if. Um, the big hint that I'm going to give you here is that there's at least one thing that is true about this triangle that you know for certain that you could mark on this diagram that we have not yet marked. I might need to check to see if my dog is committing crimes. Stand up for just one moment, but do we want one more hint before I. Actually, never mind, I heard a cabinet open, so that can't have been him. Alright, everything's fine. The big hint that I'd like to give you is it matters that this is happening in a circle, and you haven't yet used the circle for any knowledge. That's true. The circle doesn't matter because of the angles in the circle, though. It's a different property of circles. I've got one more question after this, but it's a pretty blatant one. And I'm going to be pushing you pretty hard to see if we can make this one because this is a big level up moment. It's something that comes up a lot in this sort of question. Yes, can you tell me why? Yes. They are both radii, so they must be congruent. And if there's a triangle with two congruent sides, there's a special name for that type of triangle. Isosceles. And isosceles triangles have some properties that normal triangles do not. Therefore, the equation that you originally wrote with two variables. Aha. Mm-hmm. Right. That is absolutely correct. Lovely work. Thank you for bearing with me as I pushed you pretty hard on that one. I think that that's one specific variety of breakthrough where it changes a fair amount if a student's able to make it on their own. I think it leads to meaningfully better learning. All right. Lovely work. The big upside to this one is this is clearly a question that was pretty tricky for us, but once we've made this set of connections once, it's much easier to make those connections again a second time. And those connections are relevant pretty frequently because we can draw triangles whenever we feel like it, and circles come up relatively frequently. All right, then we're on to question 14 next. So linear functions are the second most common question type in the math section, and questions like 14 are the test telling you that just because they're linear functions doesn't mean that they're necessarily easy. For this one, do you want to start with guiding questions, or do you want to start by thinking some things through on your own first? As the kids say, go for it. Mm-hmm. Mm-hmm. You are absolutely correct. Can I ask you to read the first sentence? If it's a line, it's a linear function. Yes. Lines and linear functions are you might be conflating lines with like squiggly lines could be lines, right? But in geometric definitions, lines are straight. So linear functions are the only lines you can deal with on the SAT. Possibly outside of the SAT as well, but I'd have to think harder about that to know if that's true. Uh huh. Mm-hmm. Mm-hmm. Question. If you don't have the slope formula down perfectly, can I show you a method to get through this without ever doing the slope formula ever again? This is literally the same thing that the slope formula does. It's also what the distance formula does. You can ignore both of them at the same time. You draw a right triangle. Can you tell me how far up and down this right triangle goes from 13 down to negative 15? Yep. How far right does it go from 5 down to 12? Is the slope positive or negative? And rise over 1 would be? We just calculated the numbers. Yeah. So the slope is? Right. This is literally the slope formula. This 7 is x2 minus x1. The negative 28 is y2 minus y1. But we don't have to worry about getting mixed up by a formula because this picture just makes so much more sense. If you wanted the distance between those 2 points, just do the Pythagorean theorem. And I mean very literally that the distance formula is literally just drawing this triangle for you. The distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. But those are just these side lengths. It's just saying c is the square root of a squared plus b squared. It's literally the Pythagorean theorem. This one's a little bit difficult to talk about over text. I don't know that I'm going to include this in the wrap-up email, at least in a very parsable way in there. But this sort of visual understanding of it is, I think, a very easy way of parsing this sort of thing. We're also going to show off another method to get through this afterwards. But first, can you take it home from here? Mm-hmm. You are trying to find the y value. And you're trying to find the y value when x is 0, presumably. Except that's not how it works, right? Okay. Don't you just... Okay. You plug in one of the points that you know, is how you make that work. And can you tell me what your final answer to the question would be? Lovely. Let me set up a new incognito tab for this. Give me one moment while we open up this Desmos. And I'm going to pull up a screen share. So, one of the really cool things that Desmos can do is it can actually give you the equation of a linear function from 2 points. Just sort of for free. You see this little plus button up here? We're going to use that to add a table. Now, when we add a table, this little blue bar over here is not going to have anything with it. But once we have at least 2 points in here, it will have something show up. Here we passed through, remind me, was it 5, 13? And 12. And now this little thing over here pops up. So does this thing right here. If we press this one, it changes the zoom of our graph to the point where we can see both of our points. But this top one is what we're interested in. This add regression button creates the line of best fit. Normally that's used for scatter plots. But if you only have 2 points, the line of best fit is the line that passes through exactly those 2 points. Uh-huh. Mm-hmm. Yeah, this is some really, really strong stuff. You can even theoretically do this for quadratics by going down to the quadratic regression. However, there are infinitely many quadratics that can pass through 2 points. If you're looking for a specific quadratic, then you need to provide at least 3 points. And as you can see, if we delete this point right here, then the quadratic shifts. I wonder if I can make it flip upwards. I can. Hell yeah. Okay. That's not important. Don't worry about that. There was something else I was going to say maybe, but I cannot remember it anymore. Desmos is quite strong. We want to use Desmos when it's appropriate to do so. For questions like this one, I'd love it if you're able to solve it without Desmos, because theoretically they could ask you questions that rely on you being able to do it in an appropriate way, an elegant way. But Desmos is also pretty convenient for them. I think that generally speaking, the hardest part of this question is coming to the conclusion of what K is, and you did that very cleanly. I think you just need to get a little bit more practice with setting up linear functions from 2 points, and the rest of this question would start going nice and easy. Excuse me. 16 is a tougher question. Okay. In that case, do you mind if I spend a little while talking about these hard systems of equations? So first things first, this is one that we could solve via Desmos. We could graph the line they've given us, and then we could graph each of the answer choices. And that would get us through the problem eventually. But the SAT also likes to ask variants of this question type that we can't solve via Desmos. For instance, can Desmos tell you if 2 lines are parallel? Can your eyes tell if 2 lines are parallel? The answer to that is no. No, they can't. They can tell when lines aren't parallel, but they can't tell when lines are parallel. For an example of that, I'm going to show you a mind bender of a puzzle real fast, something called the missing square puzzle. Can you figure out how this works? Everything involved is the exact same shape. Everything uses the exact same number of tiles. But when we rearrange them, there's a square missing from the bottom one. How could that be the case? The blocks that make up these triangles are exactly the same. Excuse me, the blocks that make up these figures are exactly the same. Like, we can count them specifically. We can see that this top one is 5 by 2. And it's 5 by 2 in the other one as well. We've got this one over here that's 3 by whatever, and it's 3 by whatever in the other one. And we've got this 5 with 2, and it's 5 with 2, and it's 5 with 3. Everything is exactly the same dimensions. They're actually the exact same size. Yeah. The big trick behind this one is that neither of these is a triangle. These 2 blocks have different slopes. The top picture is a quadrilateral. You can figure it out if you do the math. This top one has a slope of 2 over 5. The bottom one has a slope of 3 over 1, 2, 3, 4, 5, 6, 7, 8. 3 over 8. 3 over 8 is 0.375. 2 over 4 is 0.4. Their slopes are slightly different. It's a quadrilateral. The answer is it's not actually making an entire square. We're just changing it from being a quadrilateral to being a shape that's got a bunch of extra sides as well. It's sort of like saying, like, here's a quadrilateral. My gosh, but when I move this one tile in the quadrilateral, it's now got a different number of sides to it. What in the world has happened here? It's a mystery. That's fundamentally what's happening here. It's a really mind-bending approach to it because the shift is really, really large and it feels like there shouldn't be a shift, but it's working out fundamentally the same way. The more specific crux of it is that we're now relying on the area beneath the red triangle, right? But there's a lot more area beneath the red triangle here than there is area beneath the blue triangle. If we look beneath the blue triangle, there's a total of 15 tiles down there, and beneath the red tile, there are 16 tiles. So it's unsurprising that the things with an area of 15 have a missing square when they're trying to fill 16 areas worth of space. Yeah, it's some really, really atrocious stuff. Why can I not control Z anymore? Okay, there we go. In any case, when I say that humans can't tell the difference between slopes, this is the sort of thing that I'm talking about. Those slopes are even, like, fairly different. But if you zoom out far enough, it no longer easily tells you if they intersect. So what if they intersect 100 tiles away? In any case, though, well, actually, let's show off an example of why that's not a super good fit. If that's okay. And then I'm going to make this. How obnoxious do you want me to make this? Okay, no, I actually have to make it somewhat obnoxious. So here's two lines. 7y plus 3x equals 2, and 5y plus ax equals 0. Can you figure out the value of a that makes these lines parallel? If we were, say, using something like Desmos. Yeah. I'm also just going to be doing some math on the side so that I can tell you the right answer. So then, have you tried plugging in a few numbers? Do you have a ballpark estimation of around where it is? And that's pretty close. But tragically, if you're writing your answer as decimal form, then you need 3 decimal points of precision. So you need at least one more decimal point than what you currently have. And even then, the distinction of is it 2.13, is it 2.14, is it slightly over 2.14, is it slightly below 2.13? Those are all distinctions that are really hard to make. Like when we were comparing the two slopes for that other line, those had a difference of 7%. The difference between 2.13 and 2.14 is a difference of 0.4%. You know, it's really interesting that you bring that up. I'm calling this out because this has been on the Blue Book tests, a free response question. So let's talk about how to do this one by hand, since we will need to understand that sort of dynamic. Now, we've been talking about parallel lines. How many intersections do parallel lines have? So if a system of equations has no solutions, that means that you're dealing with two parallel lines. What if it had infinitely many solutions? Can you think of two linear functions that intersect at infinitely many places? The same line twice is the important part there. So let's take a look at simple variants of those equations. First, let's take a look at two parallel lines. Here's y equals x plus 1 and y equals x. If we solve this with elimination, what do we get? What equals what? Right. Importantly, all of the variables cancel out, and we're left with a false statement. This is our sign that our system of equations has no solutions. Here are two lines that are the same line, y equals x and y equals x. What happens if we solve these with elimination? Equals. Right. Again, all of the variables canceled out, but this time we're left with a true statement. That's our sign that we have infinite solutions. In both of these scenarios, you might notice that all of the variables canceled out. And that's what we leverage to get through this. For instance, here, we can't cancel out the x's because we don't know the value of a. But we can cancel out the y's, and if there's no solution, that must also cancel out the x's. So that'll give us something that we can leverage into understanding what the value of a is. How would we cancel out these y's with elimination? Sure. And then it sounds like we're adding them through. And when we do so, we'll wind up with 15x plus negative 7x equals something. We don't really care what the far side is. We just care that the far side hasn't canceled out. Now here, I'm sorry, minus 7ax, excuse me. Now here, if there really were no solutions, can you remind me what's supposed to happen to the x when we do this? You're right. So now all we have to do is think about what value of x makes this cancel out. Do you want to think about that abstractly, or do you want to write an equation just to figure that out? Sure. Well, here, if we had something like 2x minus 2x, it would cancel out because 2 minus 2 is 0. So if the coefficients cancel out, the x's will cancel out. So how about 15 minus 7a equals 0? So if their coefficients of x cancel out, so will the actual x's. Mm-hmm. This equation is detached from the previous equation. We don't care about the previous equation. The important part about the previous equation is that this right side hasn't canceled out, and this left side has canceled out. What we're doing here is we're setting up a new equation to figure out which value of a will make the left side cancel out. It looks very similar to the previous equation, but it is a new equation. And the far side for this one must be 0 because otherwise a wouldn't cancel out. Yeah, and if you take a look at that, your guess was pretty close. That's 2.14 and change. Yeah, I don't know that we were getting that close, but you got a lot closer than I expected. On kind variants of this question, we can get there with Desmos. On unkind variants of the question, we're probably going to need to do this. Luckily, this is a very formulaic process, and it's one where it's really, really easy to write sample problems on your own. If you want to write sample problems, and I'm going to ask you to jot this down, but if you want to write sample problems for this question type for no solutions, then you take the format ax plus by equals c, dx plus ey equals f, and you plug in numbers for c, f, and for 3 out of the other 4 variables. And you can literally just plug in whatever numbers you feel like for that. Um, for no solutions for the parallel lines, the far side doesn't matter. The important thing is that you just have 3 out of the 4 variables. If you want to write something that's dealing with infinitely many solutions, then you plug in 5 out of these 6. Since for infinitely many solutions, the far side will also cancel out. Excuse me. For infinitely many solutions, you can actually make it work as long as you plug in 4 out of these 6. With the small caveat that you can't have a pairing of them. Like you can't have both C and F, or both B and E, or both A and D. For infinitely many solutions, since the far side also cancels out, you can cancel out the far side to figure out what would cancel out both X and Y. So for instance, if you wanted to deal with the question that was 3x plus ay equals 7, bx plus 5y equals 14, what is the value of a plus b? You'd be able to do that if there's infinitely many solutions, because you could multiply this top equation by 2 times to figure out both a and b. But I digress. We've done a lot of yapping about this in the abstract. You want to lock back into this question 16? I think that there's probably a faster way of getting through this one than graphing. I'm listening. It sure does. Would that mean that C is correct or incorrect? It is indeed. So we've eliminated C. Based off of your knowledge from that, would A have no solutions? We know that it has 12y when we have 1x, right? So something like x equals 12y would be parallel, but 4y would not. What could we do to the left-hand side of the equation to make it look more like B or D? Yep. Well, I mean, don't you just take x equals 12y minus 15 and multiply both sides by 1/3? To test whether B or D is appropriate. Like, we know that C is the same thing as our equation. We've eliminated A and we've eliminated C, so B or D must be correct. So to figure out whether B or D is correct, we'd want to make the left-hand side of our equation 1/3 x, right? Mhm. Yeah, that's another way of doing it. Would B give us a solution or would D give us a solution? Wait, okay, one sec, sorry. I've come up with a different line of questions because I think that after thinking about your responses, I think I now have a stronger understanding of what you do and don't know. Is it okay if I change tack? So C is exactly the equation of our linear function. What would change C into being a parallel line? If you could change one thing about C, what would make it turn into a parallel line? A constant, right. So a parallel line is going to have the same coefficients for x and y, right? Between B and D, if you multiply both sides by 3 so that we match the x's, which would have the same coefficient for both x and y? Um, if you multiply both sides by 3, wouldn't you have x equals 36y? Sure. You'd have 1x equals 36y, not 3x equals 36y. Yes. We'd be looking for 3x equals 36y or 1x equals 12y. Hmm? If you multiply both sides, you would get 1x equals how many y? What's 4 times 3? Well, for b, what do you mean by 3 again? I want you to multiply both sides by 3 a single time. 1x equals 12y, right? Mm-hmm. Okay. Yes. And that one matches what you were looking for previously, right? It's got the same x equals 12y as c, but it's not the same line because it's been shifted up by 15 units relative to the other one. Yes. Um, so for this one, at the moment, I think doing it via Desmos is almost certainly the more consistent way for you right now. You're really close to this question right here being fast and easy, but I don't think we're going to crack it during this session. There's definitely something between you and this question quit clicking really quickly right now, and I haven't quite been able to sound out exactly what it is. Like, you're saying a lot of the things that I'm hoping to hear, and then it's just not quite coming together. We're not quite getting to the intuitive leaps that I've been trying to encourage. Um, we'll either see if we can develop this more a little bit in the future, or we'll just choose a different route through this sort of question, which is perfectly acceptable. We don't have to take this a very intuitive way. We can just do a method that takes a little bit more time and is much more consistent for you. That's also fine. These infinitely many and zero solutions are a question that you want to be pretty proficient with. They tend to show up exactly once per test. But something that shows up exactly once per test means that it's going to contribute 10 or 20 points to pretty much every single test that you take. It's very rare to have a question type that shows up that consistently on the current iteration of the SAT. The discriminant is relevant for quadratic systems of equations, but I don't think it would usually help for this one. Yes, and it tells you how many solutions a quadratic has, but it doesn't do anything to help you with linear functions. Yes. With a linear and quadratic system, if you use substitution, you can transform them into a single quadratic, and then the discriminant will tell you how many solutions that has. So what you're talking about is something that's relevant, just not for this specific variant of the question that we're talking about. So I'm not saying don't think about the discriminant. The discriminant is going to be important pretty frequently. It's just not the exact tree that we're trying to bark up here and now. I do need to make sure before we wrap things up. Are you interested in the 5 p.m. EST Tuesday and Thursday sessions this coming week? Got it, got it. This coming Thursday, my back is presumably not going to be broken in half, so that won't be an issue anymore. Okay, next time we'll polish off these last few questions, and I definitely want to make a note to iterate on this a little bit more, since I think we're fairly close to what we're looking for, and I do want to make sure it clicks, and I think it's going to require a little bit of additional instruction for us to get there. Did you know that 4 p.m. is not the same thing as 5 p.m.? It's crazy. Who came up with that? Anyways, I'm going to get that scheduled in the software. You're free to go and have a lovely night.